Hello everyone. In this video, we will learn the concepts of linear momentum and angular momentum of a particle, and we will also learn to analyze central force motion problems using the principles of angular momentum and Newton's law of universal gravitation. We are already familiar with Newton's second law, which states that if the resultant forces acting on a particle is not zero, the particle has an acceleration proportional to the magnitude and direction of the resultant force. That is, summation F is equal to m times a. From kinematics, we are also familiar that the acceleration a of a particle is equal to dv dt. If we combine the Newton's second law and the kinematic equation, since mass of a particle is a constant term, we can write that the summation of forces is the time derivative of the product mv. The product mv is called the linear momentum of a particle. Linear momentum is denoted by the letter L. It has the same direction as that of velocity, and its magnitude is equal to the product of the mass and the speed of the particle. If we denote the time derivative of linear momentum by L dot, then we get Newton's second law in the momentum form, that is summation F is equal to L dot, and this law states that the resultant of the forces acting on a particle is equal to the rate of change of linear momentum of the particle. If we consider a particle P of mass m moving with respect to an inertial or Newtonian reference frame xyz, then the linear momentum of the particle at any instant of time is defined by the vector mv. The moment of this vector mv about the origin O is called the angular momentum or moment of the particle and is denoted by HO. HO is given by the equation r cross mv, where r indicates the position vector of the particle and mv indicates the linear momentum of the particle. The angular momentum HO is perpendicular to the plane containing the vectors r and mv. The magnitude of the angular momentum HO is given by the scalar equation HO is equal to RMV sine phi, where phi is the angle between the vectors r and mv. We can determine the sense of the angular momentum HO from the sense of the linear momentum mv by applying the right-hand rule. Now let us compute the derivative of the angular momentum HO with respect to time. From the rules of differentiation, we can write HO dot is equal to R dot cross mv plus R cross mv dot. Now the first term in this equation is 0 because the vectors R dot, which is equal to v, and mv are collinear. In the second term, since mv dot is equal to ma is equal to summation of forces from Newton's second law, we can write HO dot is equal to R cross F, which represents the sum of moments of all the forces about O. This implies that the rate of change of angular momentum about O is equal to the sum of moments of all forces about O acting on a particle. That is, HO dot is equal to summation MO. Now let us look at the angular momentum equation using the polar coordinates. If we are using polar coordinates, we can resolve the linear momentum of a particle mv into its radial and transverse components mvr and mv theta. From the definition of angular momentum, we know that the magnitude of angular momentum of a particle about O is given by the equation HO is equal to RMV sine phi, where V sine phi is the transverse component of velocity in polar coordinates. Therefore, we can write HO is equal to Rm v theta, where v theta indicates the transverse component of velocity. Since we know that the transverse velocity v theta is equal to r theta dot from kinematics, therefore we can also write HO is equal to mr square theta dot. This gives the angular momentum equation in the polar coordinate form. In this slide, we will look at the motion under a central force. When the only force acting on a particle P is a force F which is directed towards or away from a fixed origin O, the particle is said to move under a central force, and the origin O is referred to as the center of force. Since the line of action of the force F passes through the origin O, therefore we can say that the moment generated by this force F on the particle P about O is equal to 0. Therefore we can write summation MO is equal to 0. Now recall from Newton's second law, we have already shown that the sum of the moments about O of the forces acting on the particle is equal to the rate of change of angular momentum HO dot of the particle about O. Now since summation MO is equal to 0, therefore this leads to HO dot is equal to 0. Integrating this equation, we get HO is equal to constant, which implies that the angular momentum of a particle moving under a central force is constant in both magnitude and direction. This is also called the principle of conservation of angular momentum. In the previous slide, we already discussed that for a particle moving under a central force, the angular momentum of the particle is constant in magnitude and direction. Therefore, from the definition of angular momentum, we can write H about O is the cross product of R, the position vector, and the linear momentum vector mv, and is equal to constant. Recall that the angular momentum vector is perpendicular to the plane containing the position vector r and the linear momentum vector mv. Therefore, its magnitude is equal to r mv sine phi, where phi is the angle between the position vector and the linear momentum vector. Therefore, the conservation of angular momentum equation can also be written as r mv sine phi is equal to r naught mv naught sine phi naught, where the subscript naught indicates the initial position, velocity, and angle of the particle. This is another form of angular momentum conservation equation, and it also applies to the motion under a central force. Since the gravitational force exerted by the Sun on the planet is a central force directed to the Sun, this equation is fundamental to the study of planetary motion. In the polar form, the angular momentum conservation equation takes the form mr square theta dot is equal to HO is equal to constant, where theta is the angle between the position vector r and the reference line along the horizontal. If we divide this equation by m on both sides, then we get another modified equation, which is r square theta dot is equal to h is equal to constant. Here the term h is also a constant and is equal to h naught over m. The term r square theta dot is twice the areal velocity, where the areal velocity of the particle is given by half r square theta dot. Therefore, for a particle moving under a central force, its areal velocity is also constant. Now let us discuss Newton's law of universal gravitation. Newton's law of universal gravitation states that two particles of masses m and small m attract each other with equal and opposite forces F and minus F, which are directed along a line joining the two particles. The common magnitude F of these two forces is given by F is equal to g times the mass of the particles divided by r square, where r indicates the distance between these two particles. Here g is a universal constant called the constant of gravitation and has a value of 66.73 times 10 to the negative 12 in the SI system and 34.4 times 10 to the negative 9 in US system. It is important to note that gravitational force exists between any pair of bodies, but its effect is appreciable only when one of the bodies have a very large mass. If we think of the motion of planets around the Sun or motion of satellites around Earth or any object falling onto the surface of the Earth, the effect of gravitational force is apparent. Now, if we consider a particle of mass m on the Earth's surface, then the gravitational force F is equal to the weight of the particle which has mass m. Therefore, we can write this equation as F is equal to W, which is the weight of the particle, is equal to m times g is equal to g m over r square. Here m indicates the mass of the Earth and r indicates capital R indicates the radius of Earth. So if we cancel out m here, what we get is an expression for small g, which is Earth's gravitational constant, which is equal to g times m over r square. The average value of g, which we use in our calculations, is 9.81 meter per second square in the SI system and 32.2 feet per second square in the US system. We should note that since the Earth is not truly spherical, the distance r from the Earth's center varies, and hence the value of W, which is weight, and g, the gravitational constant, will vary with the altitude and the latitude of the particle. Another reason to take note of is, although we consider a frame of reference fixed to the surface of the Earth as a fixed frame or Newtonian frame, but actually the frame is rotating along with the Earth. So for accuracy, a component due to Earth's centripetal acceleration should be taken into account while calculating the value of g. Now let us look at an example problem. In this example problem, it is mentioned that a satellite is launched in a direction parallel to the surface of the Earth from point A with a velocity of 18,820 miles per hour from an altitude of 240 miles. We are asked to determine the velocity of the satellite as it reaches its maximum altitude of 2,340 miles, which is point B. The radius of the Earth is given to us, which is 3,960 miles. Note that we have mentioned previously that for motion of satellites around a planet or motion of planets around a star, it is convenient to use the angular momentum approach. In this problem, our strategy is to look at the motion of the satellite around Earth. Now, Earth has a gravitational pull on the satellite. Therefore, the satellite is moving under a central force and hence its angular momentum is conserved. So our approach would be to calculate the angular momentum of the satellite at points A and B, and then equate these angular momentum values and solve for the unknown velocity at point B. So as mentioned in the previous slide, we will apply the principle of conservation of angular momentum to the satellite at points A and B. Now point A is the launching point of the satellite, so the direction of the velocity at point A is given to us. So the satellite is traveling along this direction on the elliptical path. When it reaches at point B, the direction of velocity is along this direction. So we say that the angular momentum of the satellite is conserved between points A and B. So in order to find out the angular momentum is always calculated about a point. In this case, our point will be the center of the earth. So we place our origin O at the center of the earth. So the angular momentum conservation equation then can be written as H about O at A is equal to H about O at B. Recall from the definition of angular momentum, HO is equal to R mv sine phi, where R is the radial distance from our point, mv is the linear momentum, and the angle phi is the angle between the linear momentum vector and the radial distance vector. So H about O at point A will be RA MVA sine phi A, which is equal to RB MVB sine phi B. So our M will cancel out here. Phi A is this angle, which is the angle between the radial distance and the linear momentum vector, and again phi B is this angle. So we can see that phi A is equal to phi B is equal to 90 degrees. Therefore, this term becomes equal to 1. Sine phi A and phi B are both equal to 1. The modified equation thus is RAVA is equal to RBVB. Or we can write VB is equal to RAVA over RB. Now from the problem, it is given that VA is 18,820 miles per hour. RA is the radial distance between the center O of the earth and point A. So this will be equal to the radius R of the earth plus the altitude 240. R is given to be as 3,960. So this plus 240 gives us 4,200 miles. Similarly, RB is the radius of the earth plus the altitude 2,340. So if we add 3,960, we get 6,300 miles. So substituting all these values, we get VB, which is the velocity of the satellite at point B, is equal to 4,200 times VA, which is 18,820, divided by RB, which is 6,300. And the answer is 12,546.67 miles per hour. Therefore, when the satellite reaches point B, its velocity is 12,546.67 miles per hour. Note that if we want to increase the velocity of the satellite at point B, then we can do so by decreasing this radial distance r sub b. So in order to do that, the satellite can use thrusters and push itself closer to the center of the Earth, which will reduce RB and then hence increase the velocity of the satellite. Thank you for watching this video.